Integrating with components outside of our control is one of the hardest parts of building systems. If we've got a public-facing API, we can suddenly get an influx of requests that we have no control over. And when we start to think about making our systems more sustainable, having an element of control over the compute we use and when we use it is really, really important. And this leads me to one of my favourite patterns when building asynchronous systems. And if we think about the typical API or interface, now here I have a web browser, this could equally be a message bus, input, but some kind of input that's outside of your control, a request that's coming from a different bounded context, maybe from the external world completely. And typically what we do, me included of course, is put some compute right here behind that interface. That might be an API running on a container, it might be a serverless function, but there's some element of compute sat there right behind, and then we store that data at some point. As we get more and more requests coming into our service, this compute starts to get overloaded, and maybe we add some more compute, maybe some more compute. We need to scale up our compute to handle the number of requests, and remember, these requests are something that are completely out of our control. This is a challenge because both from a scaling perspective and an efficiency perspective, but also from a reliability perspective. These servers sat in the middle here are the parts of the system that hold my application code that I've written. And I'm a human. I write greater thans instead of equals thans. I make spelling mistakes, I make typos, I write bad code. Now we're putting that bad code right directly in front of our users. So what can we do about this? How can we start to solve this challenge? Well, it's actually quite simple. We can just simply reorder this architecture ever so slightly. Instead of running the compute straight away, we can actually store the data first. So the first thing our interface is going to do is store that data durably. And this is what we know as a storage first API. So now, as more and more requests come into our system, this data is just being stored until sometime in the future when we are ready to process it. We get a sudden influx of thousands of requests. Well, we can deal with that. Our compute can deal with that. And the data is stored durably. If a response goes back to our consumer to say, happy, 200 response, okay, they can absolutely guarantee that that data's been stored. And then when we run our compute, this line changes directions. Instead, now our compute is reacting to requests as they get stored in the database, and we can start to do some really smart things here, like batching our requests up and running them at the same time. We could start scaling our compute up and down, so when there's no requests waiting in the data store, well, we can get rid of our compute completely. So let's have a look at how we can implement this kind of storage first API on AWS, and there's a few different patterns that we can use for doing that. All of the code for this is on GitHub in the Sustainable Architecture Patterns repository, but let's have a look at this implementation of a storage first API. And when we build out a storage first API on AWS, there's a few different options we have for the storage part. So for the purposes of this video, we're going to look at DynamoDB and at Amazon SQS, but this could be a whole range of different services. And the first thing we need is some kind of role. We need a role for our API gateway to assume. So we've got this integration role here that's created, and then we've actually created a construct here to allow us to dynamically switch out what we're going to use as our storage part of our storage API. And this actually takes a storage type enum in, and that storage type can be either Q or DynamoDB. So based on the storage type that is selected when using this construct, we'll either create an SQS API integration or a DynamoDB API integration, and both of these types are custom types to my application. So let's first look at how we can use SQS as a storage first API. And what we create in both cases, whether you're using SQS or Dynamo, you're going to be using this AWS integration property. So this actually does come from the AWS CDK. So the first thing we're doing in this API construct is creating our queue. We set up a queue, and then we grant that integration role we created back here. We grant that role permissions to be able to write to our queue. Remember, we don't need to read from the queue with this message. We just need to send messages onto the queue. And then we're setting up all of the integration options. So when you're setting up this integration, the important ones are that the service is SQS, the path is the path to the actual queue itself. So here this is made up of the account that this is deployed into and the name of the queue. And then we can actually set up the actual integration options. So we want to use that integration role. We want to set the header type for the request to SQS as being form. And then actually we're specifying our form data there. Remember, using a form content header. So we've got an action of send message. That's the actual API call. And then we're specifying the message body. And this uses VTL to just grab the body from the HTTP request. And we can do that using $input.body. And that's going to store the entire body of our HTTP request in our SQS queue. And that is as simple as it is to set up the SQS integration. So let's have a look at the DynamoDB one now. And if we go over to our DynamoDB integration, you'll see much of this is very similar. You know, we create a DynamoDB table instead of creating an SQS queue, and we grant write-only data to our integration role. Then we go off and create this AWS integration object, but now we have some slightly different things going on here. Of course, our service is still DynamoDB, but we're using this put item action property instead of the path property that we used for SQS. And then when we actually get into our integration options, we're actually manually creating this request template. And if you're familiar with DynamoDB, this request layout will be quite familiar to you. We specify our table name, which is the name that comes from the table above. And then we actually specify our item. Now this does get a little hard to read with the string, with escape and the double quotes, but you see we've got our partition key, and we're setting our partition key to be a string, and that string is actually going to be the request ID that comes from API Gateway. Then we're actually going to set the property in DynamoDB of request body, and we're going to set that again to a string, and that's going to be the entire contents of the HTTP body. We're going to pull that out as well, and then we're going to set this timestamp field right at the end, which is just the time the request came into API Gateway. And you can get as complex or as simple with this request template as possible. And this is just VTL. We're just specifying a combination of the DynamoDB API call, the put item API call, along with VTL to allow us to pull out things like the input and the context and the request ID and things like that. And then we'll just say return a response. If DynamoDB returns a 200 response, then we'll just return an empty JSON object. We could, of course, add some additional properties in there if we needed to. So then we set up this integration, and we've got our AWS integration now. So that means if we specify a queue, we get an SQS integration, DynamoDB, we get a DynamoDB integration. And then we actually go off and create our REST API. Now this big for each here is just dynamically adding the multiple paths to API Gateway. And the important bit really is when we add a method. So we create a resource in API. A resource is just a path, a component of the path. And then we're adding a method to that resource. We're adding a post method with our integration that is going to be either our SQS integration or our DynamoDB integration, and then we've got a few different responses for that method request. I could also say api.root.method, and I could add this method to the root of my API if I wanted to, but of course we're probably building out multiple routes on our API. When I use this in my CDK stack now, if I look at this .NET stack, and we can have a look at our storage first API here. So I'm using the storage first API construct, and I'm passing in my storage type to be a queue, the integration to be sample integration, and then the API route to be inbound SQS request. Lovely. And what I'm actually going to do before I deploy this, I've actually got a Lambda function hooked up to this SQS queue, but I'm actually going to just disable that Lambda function just for the moment so that we can see the message actually hit the queue. And I'm going to go off and redeploy that now, and then I'll come back to the video in just a moment. Okay, that's finished deploying now. So if we just open up Postman, we've got our API route there, and if I send my request in, and you see what I get back is my actual API response from SQS, and I could manipulate this with VTL in the CDK project if I wanted to. And one of the things that gets really interesting, you'll notice the response time, and it's pretty consistently between 200 and 400 milliseconds. It's a really consistent API response, and this is because all that's happening is API Gateway is talking directly to SQS, and SQS can work at massive scale and still keep that same performance and durability. So we're guaranteeing here that these messages are indefinitely stored. If SQS was offline, this API would return a non-200 response. The caller would then know that this hadn't been stored. If we just head off to the AWS console now, and I go to the SQS console, we can actually have a look at these messages in flight. So you see we've got our storage first API sample integration queue, and we've got 16 messages available. I sent a lot of messages then. If we send and receive messages, and we just poll for messages in the console, we can have a look at this and actually see that we've got the actual body of the request that has come from the body in Postman. What this enables now is you can see our compute is currently offline for whatever reason. Maybe the bug's been introduced, maybe I typed a greater than instead of a less than, and it threw the whole system out of whack. Well, all we actually get is messages just building up in our queue. Once the bug's fixed, the compute's back online, or it scales up, or however you manage the compute, these messages will be processed. Happy days, everyone is working well. And the last thing I just wanted to look at was actually the integration options that are available. So if I go off to API Gateway now and we have a look at the API that's been created, we've got our front-end API and we've got our post endpoint here, and we look at the actual integration request, and you see you've got this AWS service option. And if we look at this AWS service dropdown, you can see all of the services that we could integrate API Gateway with. Things like step functions, we can trigger a step functions workflow, or we could publish an event to EventBridge, send a message onto a Kinesis stream. There's all these different integrations that you can build using that combination of API Gateway, VTL to transform the request into something that makes sense to the consuming service, and then some kind of persistent storage. And this enables you to really start thinking asynchronously with what is typically a synchronous process. And you can even apply this to other services, things like EventBridge. If you are fully embedded in event-driven systems and you're using EventBridge, well, one of the targets of EventBridge is Lambda. You could have this same setup, but with the interface here being EventBridge. Then you get a sudden influx of 1,000 events, maybe already created events. If you've hooked a Lambda function straight up to that event stream, then your Lambda function is going to get overloaded, of course. If you put that buffer in between, that storage first integration, EventBridge to SQS, and then have Lambda consuming off that SQS queue, you'll both be more reliable and also more economical and efficient with your compute. As always, if you've enjoyed the video, please like and please subscribe, and I will see you all next time for more sustainable architecture patterns. Thanks for watching.